This video, I will be explaining additional bracket notation. In the previous video, I have explained three types of bracket notation. We are going to continue with the same bracket notations. So the fourth form of bracket notation is a bra notation, and so this is the combination. In the bra notation, we write two bras side by side to denote a tensor product of row vectors, because the bra notation is used to denote row vectors. So the bra notation, the combination of two bras, is used to denote the tensor product of row vectors. Here, let us take one example in which I am giving the two different functions. The first function is the written in the bra notation, bra psi, which is the 3 times bra 0 plus 7 times bra 1. And the second bra notation, or the second quantum state, is bra phi, which is bra 0 plus I times bra 1. What we are going to do is that we will take the tensor product of these two functions describing a quantum state. The combination of, when we write two bras side by side, they can be written in a single bra. So here we are using the single bra to denote the tensor product of psi and phi. So this is the way in which we are going to perform the tensor product of these two different functions. Let us take the first term. This is the first term from the first function, and we will multiply this first term with all the terms from the second function. So 3 bra 0 is multiplied with first 3 bra 0 is multiplied with bra 0, and we will write this as the first term in the resultant way, 3 times bra 0 0, because 1 0 is from first function, second 0 is from the second function. Now we will continue multiplying the first term from the with the second term from the second function. So it becomes 3i. This is the second term, and this becomes the 3i. 3 times 3 is from the first function, I is from the second function, and 0 is from first function, and 1 is from the second function. So 3i times bra 0 is the second term of the resultant tensor product. Now we have multiplied the first term with the all terms from the second function. Now we will continue multiplying the second term from the first function with the all elements from the second function. So this will become the third term, and this will become the fourth term. In the third term, we are multiplying 7 from the first with with 0 bra 0 from the second function. So this becomes bra 1 0. Now the fourth term is calculated like this. The 7 is from first function, I is from the second function, this one is from the first function, and this one is from the second function. So this is the way in which we perform the tensor product with bra notation. You can check whether this is correct or not by doing the same multiplication with our usual matrix multiplication. The bra psi is a row vector in which the 3 is present at the 0th position and 7 is present at the 1st position, because 3 is the coefficient of bra 0 and 7 is the coefficient of bra 1. Similarly, the row vector representation of bra phi is a row vector having two terms, 1 and I. 1 is the coefficient of bra 0 and I is the coefficient of bra 1. If we multiply these two, take the tensor product of these two row vectors, we will get 3 times phi and 7 times phi, because each term from the first row vector is multiplied with the each term from the second row vector. So, and we will get 3 times 3, 3i, 7 and 7i, which is the equivalent row vector representation of the resultant bra notation that we got by multiplying two bra functions. 3 is present at the 0th position, 3i is present at the 1 position, and 10 is present at the 7 is present at the 10 position, and 7i is present at the 11 position. So 0, 0, 1, 1, 0, and 1, 1. The fifth notation in bracket notation series is the Ket-bra notation. And this is the combination of two notations written side by side. We will first write a Ket and then we write the bra. And this is typically used to represent a matrix having n by n dimensions. And this is also known as cross product or cross product. So let us take, here we are writing a example. Here we are writing first Ket 00 and Ket 10. Ket 00 and Ket 1. Sorry, Ket 00 is the first Ket and bra 10 is the bra notation that we are taking. So Ket 00 is represented by a column vector where 1 is present at the 00 position, and bra 10 is represented by a row vector where in which 1 is present at the 10 position. And if we multiply these two, one column, because this, we can take the multiplication here, because the number of columns that are present in the first matrix is for 1. The size of the first matrix is, or size of the vector is 4 by 1, and second is 1 by 4. Here the number of columns from the first are equal to number of rows from the second, and if we multiply these two, we will get a resultant matrix having 4 by 4 dimension size, in which there will be 1. So this is the resultant matrix, of multiplying these two, one column vector and one vector, in which the 1 is present at the first row and third column. So in this way, the Ket-bra notation is used to represent a matrix or take the cross product of two notations. Now here another example in which we are going to use the Ket-bra notation. So this is the Ket function. This is the first function, Ket, which is the combined state of 3 times Ket0 plus I times Ket1. And this is the second function, but however it is written in the through Ket notation. And in order to use it, so this is the Ket0, 2 times Ket1 and 7 times Ket11. In order to use it in the Ket-bra notation, we need to take the conjugate transpose of the this function to convert it into the bra notation. So Ket phi is here converted in the third function. The Ket-bra notation is converted into the Ket notation is converted into the bra notation, which is the conjugate transpose of the Ket phi. And here the function becomes the bra 0 0, 2 times bra 0 and 7 times bra 1. Now we will multiply this Ket-bra in order to get the resultant Ket-bra notation, in which the each term from the first function, that is the psi function, we are multiplying with the each term from the bra notation. So this is the first term that we will multiply. So 3 times Ket0 is multiplied with bra 0 0, and we will get this term 3 cross 3 times 3 times 0 cross 0 0. And in order to get the second term, we are multiplying with 3 with 3 Ket0 with 2 times bra 10. So this is the second term, and we will get 6 times 0 cross 10, because 3 multiplied by 2 is 0. To get the third term, we are multiplying 3 Ket0 with 7 times bra 11, and we will get 3 multiplied by 7 21 and 0 cross 11. So this is the third term we will get. Now similarly, we will multiply now the second term from the psi function with all terms from the second function. So the second term from the psi function is I Ket1. So multiply I Ket1 with bra 0 and we will get I times 1 cross 0 0. Now I Ket0 is multiplied with 2 bra 10 to get the fifth term. So 2 times I 1 cross 10. Now the I Ket1 is multiplied with 7 times bra 11 to get the sixth term 7I 1 cross 11. So this in this way we have multiplied each term from the first Ket function with all the terms from the second bra function. And here we are using 1 bit to denote the row. We will have 2 rows. 2 to the power of 1 is 2, and here we are using 2 bits to denote the columns. So we will have the 4 columns. Now this resultant uh, function will be represented as equivalent matrix like this. So 3 is the coefficient of for the element, which is 3 will be present in the resultant matrix at 0 row and 0 column, because there is no term in the 0th row and first column 0 is written. 6 is present at the 0th row and third column, or the second if we count it from the 0, and 21 is present at the 0th column and 0th row and third column. Similarly, for the writing for the first row of the resultant matrix, we will write I at first row and 0 column. 0 we are writing because there is no term in the 1 column of the first row. 2I we are writing at first row and third column. 7I we are writing at the first row and the fourth column. So this is the way in which we perform a cross product of using the Ket-bra notation. Similarly, if we have given a matrix, we can convert it, write in it into the Ket-bra notation using. So this is one example matrix in which the size of this matrix is there are 4 rows are there and 2 columns are there. So here we will need 2 bits to denote the rows and 1 bit to denote the columns, and we can write it by following in the row wise. So because 0 we need to skip it, the 0 term, the 1 is present at the 0th row and 1 column, first column. So we are writing this first term because the 1 is present at the 0 row and first column. 0 row and first column. Now 3 is present at the 1st row and 0th column. So 3 is present at the 1 and the 0th column. Similarly, I is present at the 1 row and 1 column. I is present at the 1 row and the 1 column. Let us take the next row, and 7 is present at the 1/0th row and 0th column. 7 is present at the 1/0th row and 7th column. The fifth element is present because we are skipping the 0, is present at the 1/1th row and 1 column. So this is the fifth. So you can represent any given matrix in the using Ket-bra notation in this fashion. Now the last form of bracket notation is bra-ket, combination of bra and ket. The first bra is written and followed by a second ket notation, and this can be combined to one single angular bracket less than and greater than sign. Here we can take the matrix multiplication when the n is equal to the number of columns from the first matrix is equal to the number of rows in the first matrix, when n equal to m, and we will get the 1 by 1 means the unique value or the single value, and that's why the resultant vector is 1 by 1. It means a unit vector or a constant, or it is a scalar, and that's why bracket notation is used to perform the scalar multiplication of two vectors. Let us take some examples. Here I am writing, in the first example, I am writing bra 0 followed by ket 0. and bra0 is a row vector in which the 1 is present at the 0th position, and ket0 is a column vector in which 1 is present at the 0th position. If we take the multiplication of these two vectors, we will get 1 cross 1 plus 0 cross 0, and if we add these two things, we will get the value 1 1. So 0 0 bracket scalar product of bra0 and ket0 is always 1. So here in the second example, what we are doing is taking bra1 and ket1. In the bra1, the 1 is present at the 1th position, which is a row vector, and ket1 is the column vector. If we take the multiplication of these two, we will get a 0 0 plus 1 cross 1 or 1. Now let us take the third example in which I am writing bra0 and ket1. Bra0 and ket1. Bra0 is a row vector and ket1 is a column vector. So 1 is present at the first 0th position, and in the second term 1 is present at the 1st row. If we multiply these two matrices, we will get 1 cross 0 and 0 cross 1, which is nothing but 0. Let us take the fourth example in which I am writing bra1 followed by ket0. So bra1 is a row vector and ket0 is a column vector having 1 at the 0th position. If we take the multiplication of these two, we will get 0 cross 1 and 1 cross 0 and the term 0 0. Bracket notation, another example we will take. One more example we are going to see with respect to the bracket notations. Here the first term is the ket psi, which is equal to I times ket0 and 7 times ket1. The second function is ket phi and 3 times ket0 and ket1 plus ket1. So here we need, in order to take the scalar product of these two functions, we need to rewrite the first ket psi into bra psi by taking the complex conjugate of the psi function, which is equivalent to minus I times 0 and plus 7 times bra 1. Now these two terms can be multiplied. Individually by taking the first term from the psi function, and we will multiply with the so minus I is multiplied with the minus I times bra0 is multiplied with the 3 times ket0. So we will get the first term minus 3I 0 bra bra0 followed by ket0. For the second, minus I times bra0 and ket1. So similarly, now the second term from the psi functions, we are multiplying with all the terms from the second. So 7 times 3 becomes the 21 times bra1 followed by ket0, and 7 times ket bra1 followed by ket1, because from the previous slide we have seen that multiplication of bra unit scalar multiplication of bra0 followed by ket1 is always 1, and bra0 followed by ket1 is 0, and bra1 followed by ket0 is 0. Bra1 followed by Ket1 is 1. So we will get minus 3i plus 7. So this is the unit term or the scalar product of two functions written in first function is written in Bra notation and second function is written in the Ket notation, which is also called as the inner products. Inner products of two functions, two quantum functions described in bracket notations are non-commutative. Non-commutative means multiplication of bra alpha with Ket beta is not is equal to bra beta and Ket alpha only if all the terms are real. Otherwise, if there is any complex term, then bra alpha multiplied with Ket beta is equal to bra beta multiplied with Ket alpha, and we need to take its complex conjugate. So this is all about the bracket notations. 6 different bracket notations. Thank you.